Swayam Prabha. Digital India. Educated India.
Welcome back, everybody. We're going to talk about NMR spectroscopy problem solving. We talked about how the machine works and how it kind of puts out a graph for us. And this is a graph. So our goal is to take a formula, look at the graph, and come up with a structure, a molecular structure for this. That means what does the carbon skeleton look like and where are the functional groups. All right? So where do we start? There are some very important pieces of information in this graph. First of all, you will see always at 0 there will be something called TMS, tetramethylsilane. Okay, so tetramethylsilane is the most shielded compound that you can have that would be on a regular carbon chain, any alkane. So that's our standard, and then from there we can find out what is the chemical shift, and this is in ppm. Parts per million scale. So if you have values here, 1.2 for example, 3.4, and you want to know why this is so de-shielded, or at least more de-shielded than TMS, there is a chart that you can look up. And the chart will tell you if you're in a certain region, what are the functional groups that are possible for that region, or what are the heteroatoms that are next to those hydrogens, carbon hydrogens in that molecule. Okay, so the delta, the proton chemical shift data is really important for this. So let's look at some of these values, and I usually like to tabulate them so we have all of the data in one place and we don't miss a peak or two and waste time then, you know, trying to figure out the structure. And of course, it's not going to be right. So there are two peaks here. This is like one of the simplest. Let's call this A and B going downfield. A, B, these are the peaks. And let's then put in a delta value or a chemical shift going this way. That is going to be, one is going to be at 1.6. And the other one is going to be at 3.4. And this is delta ppm scale. Now, once we have that, then we can go look at other things. So 1.6 is typically in the alkyl range. This is probably next to a carbon. This one is 3.4, 3.5. And let's look at what else is on the molecule. That's a bromine. Well, go down the chart, and yes, alkyl bromine, 3.4 to 3.6. So that's pretty much right there. Okay, so this is B is a hydrogen that's on a carbon that's attached to a bromine, according to this. This is a carbon, CH, that's attached to another carbon. So that's the information we can get from the chemical shift, the environment, pretty much. We don't know anything about how many hydrogens are there and so on. For that, then we have to go in and look at the multiplicity and also the integral. Okay, these lines mean how many of these identical hydrogens do you have, and how, compared to the number here. So this is a relative value. From this ratio, we can figure out how many are in here. So that's another thing that we can go in and fill out. Another thing that would help us to figure out the structure is also the unsaturation. What does the unsaturation mean? Unsaturation means how many rings or double bonds do you have. So if N is the number of carbons, 2N plus 2 would be the formula for a saturated molecule. However, there may be double bonds and so on, and so therefore you would have a reduced amount of hydrogens for that. And let's see whether you do or not. Here you have 5 hydrogens, so that's M is 5, so N is 2, M is 5. Now we do make adjustments for the M by adding or subtracting numbers according to whatever the functional group is. Halogens, you add 1. nitrogen, you subtract 1. Group 6, you just leave them alone. So group 7, add 1. Group 5, take off 1. And group 6, you don't do anything. So in this case, you have 1 halogen, so you add 1 to that. Okay? So therefore, you have 5 plus 1. Let me first write the formula here. And that is going over 2. So this is 4 plus 2 is 6 minus 6 over 2. And therefore, this shows that this is a saturated formula. There are no double bonds. So we know that all of these hydrogens are on carbons that are sp3. Let's go in and do the integral. To do the integral, we take the heights and find the ratio of the heights and distribute the hydrogens along that ratio. So over here, if I measure this, you can take a ruler and do this, 8.75 centimeters. So that is A is to B is 8.75 centimeters, and this is about 5.9. So if you divide by the lowest number, this is going to be about 1.5 to 1. Well, we have 5 hydrogens here. So therefore, if you double this, this is going to be 3 to 2. And that's probably the ratio of your hydrogens. Once your ratio here is the same as the number of hydrogens, then you've achieved it. So we can put in the number of hydrogens from the integral. And this is going to be A is 3 and this is 2. Now, the other most important information that we can get from this graph, as you can see, are these 2 peaks that are blown up to show you the splitting. And we did talk about how you get splitting when you have hydrogens next door. This information is very helpful to find out how many neighboring hydrogens you have. So let's just write that down. A is a 1, 2, 3 triplet. Okay, so M is the multiplicity. That is, how many peaks do you have? So this is a triplet. And triplet we typically write as T. And if you take B, B has 1, 2, 3, 4 little mountaintops there, little peaks. So therefore, you are going to get a quartet. All right, so that's a Q. A triplet quartet, okay, you are going to see this a lot. They would always, if any of you have triplet quartet, you would have a 2 to 3 ratio. Before we go on to that, let's see what the information we can get from this multiplicity. The multiplicity itself doesn't give us much information, but if you use the n plus 1 rule, then you can find out how many neighbors you have. N is neighbors. And we can get the number of neighbors from the multiplicity. So if it's a triplet, that means you have 3 little peaks here, or 3 splittings. That means n plus 1 would be equal to the multiplicity. So the multiplicity tells you how many neighboring protons you have. On the carbon itself, the integral tells you how many hydrogens you have. But the carbon next door has got protons. And so that's what the multiplicity indicates. So triplet would be n plus 1 is a triplet, that's 3, therefore n is 2. So you have 2 neighbors for A. So A has 3 hydrogens, and that A carbon has got another neighboring carbon with 2 hydrogens. That's what it means. Over here, n plus 1 is 4, quartet. Therefore, n is going to be 3. You have 3 neighboring hydrogens. So I can say 3H next door, on next carbon. Here, 2 hydrogens on next carbon. That's what it means. All right, so now we got to piece this all together. No double bonds. You have 5 hydrogens. All of them are showing up here. So there's really, if you have identical environments through symmetry, then you would have fewer peaks. But here, for every carbon, you have a peak. That means there is no symmetry on the molecule. So let's draw this out. So let's put A and B here. And this is not for the carbons, this is for the hydrogens. So one of them has 3 hydrogens, that's what it means, CH3. If you have 3 hydrogens on A, then they're all identical. And these are 2 bonds apart. And you don't see 2 bond couplings so on an NMR. That means these won't split each other. Only the neighboring hydrogens would split each other. So these protons at some point would be parallel to this and aligned with this. And so there's a chance that these 2 hydrogens can be aligned. So over here, if you didn't have any neighbors, you'll just get 1 peak for this. All of these would register as 1 peak. If you didn't have any B protons, you would get a singlet. But since you have 2 of these B protons, you will have 3 different environments. One where these can be spinning both in the same direction or opposite. When they are in the same direction, they can enhance the field. When they're in opposite direction, they can reduce the amount of field that's seen. There's also a possibility that one can be up, HB1 can be up and HB2 can be down. There's a possibility that HB2 can be down and HB1 can be up. All right. So these are the possibilities for HB1 and HB2 for your neighboring protons on A. And typically there'll be an equal amount of shift for both of them. That is called the coupling constant. The coupling constant here is about 6 to 8 in an alkane. And so especially since you have CH, these are really fixed coupling constant. So you can have, instead of a singlet, because of these 2 having different environments, you can have a triplet. And it's going to be in the ratio 1 to 2 to 1 height because of the probability. So most of the time, there's twice the probability of it being in this orientation than in either this or this. So you'll have a 1 to 2 to 1 ratio on a triplet. So this is going to be a very symmetric triplet. And the coupling constants here are going to be 7.5, 6 to 8, let's say around 7 hertz. And same here. So they will be very symmetric. That's called J. And so this is JAB would be 6 to 8 hertz. You would see the exact same thing when you have a peak for HB. All right. So you can see for HB, if you don't have any neighbors, you would get 1 peak. However, you have 3 of these. So they can all be 3 up, 3 down, or you can have 2 situations where 2 of them are up, 1 down, or 2 down, 1 up. So therefore, you would get a peak that is a 1 to 3 to 3 to 1. And you would have the same coupling constants. And so therefore, this is going to be where 3 plus 1 would give you 4, a quartet. The 3 here is from number of neighboring hydrogens, n plus 1. N is the number of neighbors. All right. So great. So where do we go with the bromine here? Well, if you look at this chart, it says if you have an alkyl bromide, the hydrogen that's directly attached to the carbon bearing the bromine has a chemical shift of 3.4 to 3.6 ppm. And that's pretty much what we see here. So B, which is this, is attached to a bromine, and we can say that from our delta values. So that would kind of conclude how you solved a problem that's, a really simple one, using all the data to give you the exact structure. It's impossible to do this with IR, and well, mass spec you could, but this is really a more straightforward method. Let's look at another one over here. We have pretty much a very simple molecule, C2H6O, and there is an oxygen there. So let's say the first thing to do, usually a good idea to start with the omega values. So the omega value for that is going to be same formula as here. There's 2 times 2 plus 2 minus m, oxygen, you don't add or subtract, m is 6 over 2. So this is 6 minus 6 over 2, 0. No pi bonds here or rings here. That's one, useful information, especially if you have big molecules, that would help. Let's do the same thing over again. Let's fill this out. Let's label this A, B, and C. A, B, C, and these are your peaks. Delta is just the shift from TMS, which is 1.2 for the first one, A, and over here 3.7 for the second one, and 3.9. Now that gives us the chemical shift. So you know that these are on very electronegative or next to electronegative atoms. This one is probably just an alkyl chain. Let's look at the ratio between these, and for that we need to take the heights of those and find a ratio, and we've done this now with that one. Let's do the same thing over here. That is going to be about 8.9, and this is about 6.2, and this is about 2.9. Let's divide by the lowest number here. And well, since we have a whole number 6, it has to be a ratio that will add up to 6 for the protons. So let's say if I do 1 to 2 to 3, that's 6 protons. Okay, so therefore this is the number of hydrogens. This is coming from the integral, which the machine will draw at the very end. And so here you're going 3 to 2 to 1. That's a very important piece of information. Next thing is, again, multiplicity. The multiplicity is mainly to find how many neighbors you have. This is a big triplet. You can see there's just 3 mountain peaks. This is 1, 2, 3, 4, a quartet, and this is just a singlet. Well, let's look at the number of neighbors. N is the neighbors. This is a very important piece of information. And how do you find the neighbors? Just use the n plus 1 rule. So if you had over here 2 protons, 2 plus 1 would become a triplet. 3 protons, 3 plus 1 would become a quartet for the neighboring hydrogen. It's for the neighboring proton. Okay, so that's something to remember, because initially at least students try to think that N is the number of hydrogens on that carbon. No, it's not on that carbon, it's on the neighboring carbons. Okay, because you can have septet, sextet, on all of that. So that it's impossible to have 6 and 7 hydrogens on a carbon. So it's got to be the neighboring carbon. So triplet means N plus 1 is 3. So N is 2. So A, which has 3 hydrogens, has 2 neighbors. Over here, N plus 1 is 4. So N is 3. That means B, which has 2 hydrogens, has 3 neighbors. So that kind of makes sense, because your neighbors and the number of protons here seem to be the same. But then where does this hydrogen come in? It doesn't seem to have any neighbors. Where is it? All by itself somewhere. Let's look at it. N plus 1 is 1. Therefore, number of neighbors is 0. No neighbors. All right. So let's look at these values, guys. So here's 1.2. That's probably and it says 3 hydrogens in the same place. So these could be all just like before on the same carbon. This could be a CH3. This is going to be a carbon that has 2 hydrogens is CH2. Next thing is, are they next to each other? Well, if you have a neighbor with 3 hydrogens, you would be a quartet. If you have a neighbor that has 2 hydrogens, you will be a triplet. And there you go, triplet, quartet. So obviously, yes, they are neighbors. Well, what do you do with the oxygen? Well, let's look at that. Over here, you'll have a chart, and the chart says if you have an OH proton, that is going to be anywhere between 0.5 to 6. So 0.5 to 6, anywhere in this region. It's really variable. Why is that? Because there can be a lot of differences due to, or variability due to hydrogen bonding, the bond length, all of these can shift and exchange. So the oxygen, because it's hydrogen bonded, and depending on, again, the dilution and so many other, the amount of hydrogen bonding, you would have no splitting between this hydrogen and this most of the time. If you have a very powerful magnet and a very powerful machine, you may be able to see a 2 + 1, 3 triplet for this. Sometimes you do, but most cases you don't. We have only 3 elements, remember, that do hydrogen bonding: OH, NH, and FH. OH, NH, in this case, well, we don't really have FH in here, but these hydrogen bond. So therefore, you won't mostly have visible splitting. If you have a brand new bottle sometimes and it's not exposed to water or acids, then you may be able to see it on in a very powerful machine, but typically you don't. Therefore, this is going to be your singlet. One little thing, guys. So when you have hydrogen bonding, these protons can exchange with D2O because they are kind of loosely held. They can come off, and let's say you have alcohol and you add to this D2O, which is deuterated water, DOD. Instead of hydrogen, which has 1 proton, deuterium has 1 proton and 1 neutron. And this can exchange. So over here, you can go and get a deuterium on the alcohol. So it's deuterated alcohol. And well, this could become then HOD, head of department. But over here, that is very significant here, because if you have a peak here for a broad peak, let's say like this, and you don't know what it is and you're suspecting it's from the alcohol, all you do is put a drop of D2O, shake it up, and run an NMR if your sample is dilute, or run an NMR with the sample in D2O. D2O is a solvent that's commonly used. CdCl3 is the most commonly used solvent, and this would probably be the next most common solvent. Another one, even RNH2 can exchange, same with other acidic protons like carboxylic acid, RCOOH, although these are very, very de-shielded, about 10, so it's easy to identify them. You can still confirm that by doing, a exchange with D2O. And again, we can do the same thing with amines. Okay, so just a little note there to say how you can detect and confirm the presence of OH groups in your molecule. Basically do a D2O exchange. So in summary, we have 2 very similar molecules here. The only difference is this one has a bromine and this one has a hydroxyl, and so therefore the hydroxyl has got an extra peak here. But if you have an ethyl, this is the take home from it, all ethyl groups will give you a triplet quartet. CH3, CH2 will give you always a triplet quartet. And usually the quartet is what's linked to, let's say, an withdrawing group or a functional group, and these tend to be more de-shielded than this. So this would have a lower ppm value, and this would be a higher ppm value. This would always be together on a spectrum, and if you have lots of other molecules, they won't always be next to each other. One may be here, one may be here, but you can draw conclusions to the structure of ethyl if you have both of them in a 2:3 ratio. That's what's important. So we are going to see some trends. This is ethyl. We will look at isopropyl, propyl, butyls, and so on. So you can, when you see these trends, you see a triplet quartet, you know there's an ethyl in the molecule. All right. Talk to you guys soon, and we will come up with more compounds for you. Bye.